The honor of introducing our next speaker with perhaps one of the most intriguing conference talk titles, How to Learn a Language Without Ever Using It. So if you've wondered that, perhaps this next talk is for you. We're going to hear from perhaps the only Unison community member to learn Unison from our Haskell source files, Kyle Gates. Please welcome Kyle.
Hello, everybody. So my talk is creatively called How to Learn a Language Without Ever Using It. I was a little worried about the title because I think it somewhat implies that you never need to use it after you've learned it, which is not what I'd like to advertise about Unison. I really like programming in it. It's a lot of fun. However, my journey to using Unison was a bit roundabout because I set some ambitious goals for myself before I would let myself use it. And those led me to learning most of the syntax for the language before I'd written anything more than a few sample functions just to, get my feet wet. And I'll talk about that today. So very briefly about me, my name is Kyle Goetz. I studied pure math at university and Japanese, which is a human language, not a programming language, but language nonetheless, which is relevant for parsing them and understanding them. I lived abroad for a while, came back, went to law school, ended up working for a tech consulting firm as general counsel, retired, and now I am a stay-at-home dad whose hobby is Unison at the moment. So here, that's what I do. And before I go too much further into how I wrote a language parser for Unison that can be used in syntax highlighting and IDEs and so forth, I want to clarify a little bit of terminology I'll be using about parsing languages. There's really not that much complicated to know as far as terminology. There are tokens, then you tokenize, and you have a syntax tree. There's concrete and abstract syntax trees. We won't worry about the distinction here, and you parse a language. So the first step when you have source code and you're going to parse it is you tokenize it, which essentially is iterating through every character in your file and using various rules for that language to identify what is this word in the language. You have keywords, in the case of Unison, ability, structural, unique. You have operators, which there are rules about what punctuation can be in an operator. You have identifiers, which can end with a hash. Some hashes are a hash followed by, I think, base 16 encoded text. Some hashes are actually two octothorpes followed by just a string, and these are the built-ins, like the hash for nat is hash hash nat, because it's defined in the Haskell source code. You also, for some languages, need to concern yourself with line terminators and indents because indentation might matter. This is Python. Unison is another one like that because our code blocks, the beginning of a code block either needs to be in line or it needs to be indented more than the previous line of code. So we track indents as a type of word in the language. Comment, string literals, text literals. So you'll iterate through character by character. And for example, if you see a carriage return or a new line character, then we admit that from this iteration as a line terminator. Or if we see a double quotation mark, then let's assume we're parsing a string literal and consume characters in this character stream until we hit another double quotation mark that is not preceded by a backslash, which would just be an escaped character and not the end of the string, not the end of the text. Once you've gone through all of the source code and tokenized it, well, that's what tokenizing is, you end up with, this is a visual representation of what you end up with. If you've got a use clause where you're using use nat plus plus new line, it'll be tokenized as reserved use, identifier nat, identifier plus plus, and a line terminator. But crucially, tokenizing does not enforce syntax rules. That is what's done by the parser. the parser takes your stream of tokens and it converts it into a data type that represents the tree of your source code, how things actually relate to each other on a syntactic level. As a simple example, one might define your entire Scratch file as a data type Unison code, which contains a list of things permitted at the top level. And in Unison, those things are a use clause, a type definition, an ability or type declaration, an ability declaration, a watch expression, a test expression, which is actually a special case of the watch expression, and type declarations, and folds and comments. I think that's pretty much it at the top level. So you would be proceeding through your tokens, trying to apply these rules. If you don't have an active rule you're working through right now, but you come across the reserved word use, well, the only place that occurs is in a use clause. So you might trigger some logic to begin parsing a use clause. Well, we've got this reserved word, and then the next thing is a mandatory namespace that we're importing from, and that can be letters, letters dot more letters. It can have this hash at the end. That's what the tokenization has done. It's given us an identifier. And then we consume every additional identifier until we hit a line terminator. And that's how you would parse a use clause. Then you just drop it in your custom data type representing a use clause. You'll note on the second to last line of the slide, the use clause type in there does not have the word use. And that's because we can reconstruct the use clause just from that data. We don't need to store that one of the tokens was use because we don't need it anymore. So you can also think of parsing as throwing away what is no longer needed because it's implied by the structure of the tree itself. And that entire activity is called parsing. So there are two approaches to parsing, two broad categories. There's batch parsing and incremental parsing. When you batch parse, compilers do this a lot. The logic is simpler than incremental parsing. The result of parsing is just a success or failure. And the failure ideally will have a reason why it failed. The first thing it ran into that was not parsable. And examples of batch parsers include Parsec and Megaparsec and Haskell. Uniparsec is something Stu wrote. I don't know if he's in the chat, but thank you for that. He wrote that, and it's also a batch parser as well. Contrasting this with incremental parsers, which are faster. The name's descriptive of what it is. It parses incrementally and on the fly. So the logic to do this is more complicated, and it's newer. Batch parsing has been done a lot longer. Incremental parsing, there have been some academic papers that have come out. I think maybe a decade ago, there was one about an idea called LR parsing that became a really big deal and made incremental parsing just blazingly fast. This is actually used by tree sitter, which is what I'll get to in a bit. A nice thing about incremental parsing is that depending on how bad the parsing errors are, the errors in the code that the programmer has written, it might be able to produce like 90% still parsed, and then there's one node somewhere that is an error, and it'll tell you where this error begins and ends. So it's useful for actually alerting a developer if you've written a plugin for an IDE that uses a tree sitter or another incremental parser. A couple examples are tree sitter and then attoparsec in Haskell. It's an apt name because an attosecond is even faster than a nanosecond, so it implies that it's very fast. And these are useful in IDEs because they're much faster for parsing code. So that's the introduction about how parsing works. But let's actually take a look at what Unison is parsed under the hood. In Unison, it's the megaparsec is the language used to parse the code in UCM. And there are some key files that do the parsing for you. And actually, like to take a look at a little about that with you just to show you an idea of what it looks like. This is the term parser file. And the important thing I'd like to show here is just um, this is an example of one of the parsers. Understanding how the monads and everything work together is less important than logic at broad strokes. When you're dealing with the imports in a file, the first thing you want to look for is this reserved word used. You're going to look ahead to it because why try to parse if you don't even see that as the next token. And if you do see it, then you need to look at ones that are separated by a semicolon, which is in this case implied by the line terminator. So it's a virtual semicolon. And you collect all the names and reconstruct from there this use clause. And there are, I won't get into this one. This is going to be a lot more complicated, but here's a block parser that is concerned with whether it's the top level, whether there's an implied unit at the end, takes all these parameters. But it's very similar that if you recall from writing Unison, if you have a term, you have the term name optional parameters if it's a function, an equal sign, and then after the equal sign, you start a block. A block can start on the next line with an additional indentation, or it can actually be inline. But then the first thing in a term that you can have is more imports, more use clauses. So that's like the first thing we see here after you open the block. And then you grab all of the statements that are separated by a semicolon, which can be a virtual one. In that case, it's like a new line. And then you close the block. And then further, then there's more complications about what a statement can be. They can be destructuring binds, variable assignments, function calls, all that kind of thing, as long as the function returns a unit. But that's it. The UCM code continues on quite a lot for all the different rules in Unison. There's also another file for parsing terms, or for parsing types as well. I won't get into that. But that is how the Unison works. Tree sitter is written in C, but tree sitter is actually two different products together. It's a language parser that uses one of these tree sitter grammars you've created to parse input source code. It is also a parser generator. So you can write using a DSL of theirs in JavaScript, you can write rules for parsing that is not the actual parser, and then it will convert what you've written into C code with, I believe, Rust bindings and some Python bindings, Node bindings, and a JSON file that is a transformation of all the rules you've created that then the tree sitter code itself can use to just quickly do parsing. I've talked about the use clause because it's a relatively simple one to describe, but so I'll move beyond that. The tree sitter works great for this. Let me find here we go. So this is the tree sitter grammar for Unison. I hope that the text is big enough. Let's see if I can make it bigger. Yes. But the meat of the DSL here is we define externals, which you can think of them as problematic tokens in a language, ones that tree sitter cannot intelligently handle on its own. So you have to get in and write custom code for. You can see here there's semicolons, starts, and ends, which I'll get into why you need those in a bit. Extras are things that can appear anywhere. A comment is really the only thing that can appear anywhere other than a white space in Unison. Everything else is pretty strictly defined. And then we have our entry point here, Unison. Unison's grammar is just a repetition of, as I said, watch expressions, tests, type declarations, terms, folds, use clauses, and ability declarations. And that's it. So if you are working with, let's say, an ability declaration, um, as the you're going to go parse one of those, the code gets rather complicated. But when you take the time to read it, it's easy to understand. You look for patterns in the tokens, such as an open brace, which always indicates the beginning of a list of effects in a type signature. And then you parse comma-separated identifiers as ability names until you hit a closing brace. Much of everything else operates the same way. They call each other. It's recursive because your types can involve other types in the type constructor side of things. So it could be tough to write that logically yourself in C or whichever language you're writing the parser in, but luckily TreeSitter handles that for you. Now I mentioned that there are some problematic tokens, and one of those is a fold. And that is because a fold must begin on the first line of a source code line. It's 3 dashes and then a new line character. You might think, well, we'll just scan for dash 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 new line, or even use a regular expression. The boundary of the beginning of a line, dash dash dash, boundary of the end of the line. But the DSL for TreeSitter does not allow you to use boundary tokens in your regular expressions, which means that's out the window. Fortunately, TreeSitter provides a hook in. You can write some custom C or C++ code that will let you to more granularly work with not the tokens, but actually the incoming character stream to produce your own tokens. So this is what that code looks like. It's a lot of C because there's a lot to handle. Even though it really doesn't handle recognizing that much, it's just you have to manually worry about all the exceptions here. When TreeSitter is fired up to parse some source code, the first thing it does is it creates any state that you need. Fortunately for Unison, we only need to track indents. TreeSitter cannot track those, so we have to track them to make sure when we begin a code block that we have further indented the code or equivalently indented the code compared to the previous line. So we generate some state, and then as it proceeds through the tokens of the source code stream, through the characters of the source code stream, it begins with this evaluation function, this top level function. It will take the state that the first time we fired it up, initialize it as there's no indentation, and then it will just start processing token after token after token. And in the case of a fold, the first thing we look at is does this, and fold is actually called from a function called new line. So the only way we invoke this fold tokenizer is if we know that the previous character was a new line character. And this is all handled in the C. So we look for a couple of hyphens, but then I mentioned that it's more complicated than just, oh yeah, this is just pull 3 dashes and there's your fold. We have to make sure that we're dealing with a fold and not just a regular comment. So we only pull 2 dashes, and then we peek at the next character, and if it's a dash, it's a fold. If it's not another dash, then we're dealing with a comment. We have to handle, well, what if it's a new line here? But then otherwise we recognize it as a comment. And this is like a tokenization step done in the C. And the end result is the control then gets handed back to TreeSitter itself, which sees that the token recognized was, we actually output from we call it a comment in the JavaScript, but it sees that a comment was spotted. And in this definition we have of what's permitted where in the code, it looks to see if comment was a token that was permitted there. And if so, then it proceeds. It says, well, this was a comment, and it proceeds past that step in parsing. And the end result is parsing that is very fast. Let's take this sample unison here. I just defined a type, a unison token with some type of various type constructors, a fold, and then a bunch of code here that we're ideally, nothing's, it should all just be treated as a fold. And indeed, if I run the tree sitter with the parse command on that source code, the output it gives is, oh, I see. I think it's had an extra semicolon in the C and it regenerated. But here's the output for it. This you can think of as tree sitter's visual representation of the syntax tree. You recall that first property I showed you in that JavaScript file was Unison. That's the entry point for parsing. And the top level things that were available were fold, type declaration, term definition, and so forth. The result here of parsing is it recognizes that first bit was indeed a type definition, type declaration. It goes from line 0, column 0 to line 8, column 21. The first thing you have is the type keyword. If I'd actually called this unique type instead of type, it would have also detected the unique keyword. And then we begin this type constructor, which is a type name that in this case is just one wordy ID, unison token. There are no type parameters here. If I put those there, then it would parse differently. And then the next thing it recognizes the equals symbol. And then a series of wordy IDs. These are just identifiers that are words instead of symbols, which would be operators. Pipe, and then another constructor, a pipe, another constructor, and it continues on until line 8. And then sure enough, here we detect a fold that goes from line 10 to line 30, which is line 10. Well, this is one index to the other 0 index, so line 10 all the way to line 31. So that's how tree sitter works. And you saw it's fast. Let's see how this works. If I can do this, edit namespace, lib, base, nat. So let's dump a bunch to the screen. I was probably going to have some errors because I discovered an error in the parser yesterday. But you can see how absolutely long this file is after dumping the namespace in, a few thousand characters. If I parse with demo, it's done already, just immediately. So you can imagine for when you are in an IDE developing, if you can parse thousands of lines of code to do syntax highlighting, that works great. And indeed, I'm in Z right here. You can see. Oh, so first of all, I do want to shout out to ZetaShift, who I saw in the chat earlier, incorporated the parser into Z, which is an IDE. You can see that there's code highlighting happening here. We have the function calls, reserved words like do and use that are a slightly different color purple in my theme. Then some of the function calls is even size to abort. The punctuation is unobtrusive, default black. And yeah, you saw it's quite fast that way. And so thank you to ZetaShift for incorporating into Z. I'd gotten into this because I wanted to use my tree sitter in an IDE called Laps, which is a Rust-based one in alpha release when I started, but they actually closed off new parser submissions before I finished writing it. And they're not dynamically included. They're hard-coded into the source code. So unfortunately, that one doesn't get Unison support. But that's what motivated all this. And yeah, that's how tree sitter works. And what can you do with the syntax tree? I suppose I have enough time to just briefly talk about that. We've already talked about syntax highlighting, which you might not even really need the parser to do. The lexing is often enough, or the tokenizing. You could just have simple rules like an identifier gets colored green. If it's a reserved word, color it blue. If it's a string literal, color it green. If it's a comment, desaturate. give it partial transparency, italicize it, whatever logic the IDE's syntax highlighting plugin wants to do with it, it can do it because it knows what token we're working with. So that's pretty straightforward. Code folding is another one you can do with the syntax tree. You define which tokens or which nodes in your syntax tree should be foldable, and Unison probably folds multi-line comments, blocks of code, functions. Doc blocks would be another that would be nice to be able to fold. And wherever those are in the syntax tree, you pair those up with which lines of the IDE's window you're dealing with. And if it's foldable, put the little expand contract button. And if a user clicks it, then you refer back to your syntax tree. Recall that it says what line and column a node begins and ends on. And you just don't render any of the lines of that source code except for the first one, which maybe you italicize and add an ellipsis at the end to indicate that it's been collapsed. You can also refactor code, which is a little more complicated, but not that bad. If a user clicks on an ident, first you have to decide what is refactorable, say renameable, and those would be identifiers. So if a user right-clicks on anything that's not an identifier, don't present that option in the IDE to rename it. But if it's an identifier, say pop up a modal window, ask them what they want to rename it to, and then you find that specific node in the syntax tree that representing that place that they clicked, and that's the thing you're going to be replacing the name by. You might think, well, why don't we just traverse the entire tree, accumulate every occurrence of identifier, foo, or something, and do a name replacement there. The reason you can't do it is because of scoping enclosures and variable shadowing. If you have some parent function using a variable foo and then a child function instantiates its own variable with the same name, you don't change them both. You'd be changing only one of them. So you traverse from the one you've discovered that they want to rename. You traverse up the syntax tree until you either reach the top or you reach where that variable is instantiated. You look for another node that you've probably called something like variable assignment. And once you've reached that, you can't go any higher because the variable will not exist any higher than that. That's your parent node. Now you traverse the entire tree that is rooted at that parent node and accumulate every appearance of that variable. And if on some branch you hit another variable assignment that does another variable shadowing, you stop traversing that subtree. So anyway, you accumulate all of these identifiers, and then for every single one, you do that name replacement. And then re-render your source code in the IDE based on that. So you've updated your syntax tree, you've updated the source code. And that's how it works. Minification is another use of syntax of the parsing, but it's really just a fold operation over renaming variables, which we just talked about. You accumulate a list of every identifier in your source code. You count how many characters long the name of the variable is, how many times it occurs, and you multiply those together, and that tells you how many bytes of text that variable name is responsible for in your source code. You do a descending sort on the size. And then for the first one at the top, let's say it's a 10-letter long variable that appears 50 times in code. That's 500 bytes of text just from the variable name. Give it a variable name A or B, just something very short, and do that replacement everywhere. Move on to the second highest ranking, take the next available short variable name, do the same thing. And you just fold, it's just a fold of a renaming operation. And the end result is also, if you strip out white space and things like that, the end result is code that is one line long. The variable names are all very short, and you can shrink your source code a whole lot. You can get real sophisticated in Unison, for example. Well, Unison, since it's all hash and you're not distributing source code over the web to execute it in browsers, it's a little different. But if it's something like JavaScript, You can get sophisticated and built-in functions. You can create short aliases for them as well. So even if it's a yeah, so you can create aliases for them and you just iterate, you just do the minification the same way. So those are some uses of parsing that you can do. Tree Sitter enables all of them, just somebody has to step up and write plugins for IDEs that do them. I haven't seen one for refactoring yet. Code folding may be something that I do soon because it's pretty straightforward. That's what you can do. I had thought about writing a toy parser for JavaScript in Unison using Stu's uniparsec, but I know my time is coming to an end, so it's probably better for everybody that you don't have to sit through me fumbling around like that. But that where what I showed y'all, was it here? This code that I parsed is the beginning of one. If we were writing a parser in Unison, you have a Unison token, and um, you think about what are all the tokens in Unison. You have identifiers, reserved operators, folds, comments. Usually you'll have literal text, literal nats, literal ints, and so forth. But then you progress through the characters like I described earlier and tokenize it, and then you'd invoke your parser, which has rules like top level is a use clause. So if you see a use, look for, you know, grab every identifier token until you hit a line terminator, and you can reconstruct that use clause object. But alas, there's no time for that. I can take questions, but I believe I'm taking them in a separate room.
Yes, wow. Thank you so much, Kyle. This is you're the human documentation of our grammar
Yeah.
because for folks who don't know, Kyle came and did this on his own, and by asking us questions, really helped formalize some of that. So I'm super excited that you've presented and shared some of this, some of what you've learned.